we have a really exciting next talk where we'll hear from Professor Michael Bronstein, who is the chair in machine learning and pattern recognition, and most notably, he developed a startup called Fabula AI that he just sold to Twitter. So he is there as the head of graph learning. So we will hear now from his perspective on how actually technology can help with fake news detection.
Thank you very much. So I should probably hide myself and feel ashamed after the previous talk, basically getting myself rich. And working for, well, fortunately for one of the companies that was not on Toazo's blacklist. I hope so. Yeah, so I also work for Twitter now, not only for Imperial College. And I wanted to talk about basically more academic research and how it has led to some commercial technology that as it was mentioned, was acquired recently by Twitter. And the topic of the talk is what we call geometric deep learning. So I guess in this audience, all of you have heard about deep learning. So that's, well, if my clicker would be working, that would be great as well. Yeah, so deep learning is basically almost a household term. It's a very prominent buzzword in the latest years. And actually, it is a pretty old thing, right? If you look at the history of what is now called deep learning, it is at least 50 years old. Some of the first results on artificial neural networks go back to the 50s or the 60s. And the breakthrough, the paradigm change that it has brought is relatively recent. We can talk about less than a decade. And the driving forces of this transformation have been the computation, basically the growing power of computing hardware, the advances in algorithms, and also the availability of large scale data sets, what is known as another buzzword, the big data. And this has brought really a big change in many fields, including computer vision, which is one of my fields of research. You can find deep learning now as a commercial technology, for example, powering self-driving cars, many applications in natural language processing, speech recognition. So if you talk to your iPhone, there is deep learning that is powering these capabilities. And also, more recently, very interesting applications in other sectors, such as healthcare, such as drug design and development, which is still a very early emerging technology, but looks like a huge potential for making a breakthrough. So taking the example of computer vision, this is a kind of a poster child, if you wish, of deep learning. This is where probably it had the most prominent impact on the field. Some people call the classical methods BDL, before deep learning. So basically it was based on handcrafted features. You will take an image and you try to extract some very carefully engineered representation of the data and then feed it into some simple and easily interpretable algorithm that will tell that, for example, this is a face. And this is how early algorithms, for example, for face detection that went into digital cameras about 20 years ago were working. It turned out that it is very difficult to design these handcrafted features for any kind of data. So the paradigm change that happened with deep learning is actually to learn these features automatically from the data, basically by a black box that essentially goes through an optimization problem and has a lot of knobs, a lot of parameters that you tune, and you get the features that are optimal for your data, for your task. And this made a big difference in computer vision, in other fields as well, speech recognition, natural language processing. And one of the challenges is that most of the data that this field has dealt with is what we call Euclidean structured data, like images or acoustic signals or text. You can think of them as basically as grids, one-dimensional grids, two-dimensional grids, whereas many other applications involve data that has a different structure, like social networks, for example. So this is network structured data. In computer science, we call these graphs. So in a social network like Facebook or Twitter, you can represent your data sets as graphs where the nodes are users and social connections are what is called edges. And actually, graphs are very universal models for systems of relations or interactions between things. So you can think of problems in, for example, in chemistry, where you can represent molecules as graphs. You can represent different interaction networks, for example, in human brain imaging. So this is really a very widely, almost ubiquitously used model for different systems of interaction. So that's why developing the capability of dealing with this kind of data, basically going beyond the Euclidean structured data, might be extremely important and bring the deep learning impact into fields where the data has a different nature. So this is what we call geometric deep learning, some other terms, graph representation learning, network-based AI, if you like buzzwords. I don't like the term AI because I don't understand what it is. I do understand what machine learning is, but not AI, right? And well, Nick is a professor of artificial intelligence, can probably tell more about this. So I will show you this example. So can you go back? And yeah, so what you see here is actually what is called motion capture. So it's a particular type of computer vision, computer graphics problem where you see an actor performing in front of a 3D sensor, and the motion of this face is transferred to this digital avatar. And this is technology that is used in movie production. Obviously, in movies, it's way bigger and way more expensive. So this is a very cheap 3D sensor that you can now buy for something like $20 or $30. And basically, this is happening in real time without any fancy hardware. That was a Swiss company that was acquired by Apple a few years ago. And now, for example, the Animoji in iPhone 10 and next generations are powered by this technology. So if you look at this problem, basically here we also have the input is geometric data. Basically, it's a surface or a point cloud that represents the human face, and we need basically to do some analysis. Basically, we need to do machine learning on this kind of data. Next, please. So here, in particular, we are dealing with two types of problem. One of them is analysis. Basically, it's finding the correspondence of the noisy input to some canonical human face, and the synthesis is basically creating this virtual human model that appears like Shrek-like creature in the previous video. Next, please. So the challenge in creating this kind of capability, basically using deep learning models for this type of data, is that we need to replace the standard operations that are used in deep learning systems, in particular in convolutional neural networks, with the analogy that works on geometric data. Can we skip a couple of slides? Yeah, you can skip to the next one and next one as well. So this is an example of what was doable about 4 or 5 years ago. So we developed some of the first neural networks that worked on this kind of geometric data in computer vision, computer graphics. You can see here example of correspondence problem where we can find very accurate mapping between these different shapes. So same thing works for faces or for hands and other parts of the human body. So these were state-of-the-art results at the time. And go to the next slide. So this is another startup company with colleagues from Imperial, so I'm actually not involved in this company, but they're using our technology. Basically, this is a 3D avatar that is constructed from 2D video. So imagine that you can use it for applications like measuring your body, and for example, digital platforms like Amazon can suggest you, for example, what would be the right dress for you, or maybe even show you, like in a virtual mirror, wearing a new outfit and basically doing it in real time, actually without using any 3D sensor. So that's an interesting thing that in 2012, when I showed you this example of the markerless motion capture, I was involved in another startup that was acquired by Intel. We were developing 3D sensing technology, and at that time we believed that that was necessary and crucial to make these kind of applications. Nowadays you don't need any 3D input to get the same results, and it's all because now we have advanced deep learning technology. Next, please. So I mentioned this maybe as an example of geometric data, but what is really interesting and probably more prominent and much richer kind of data is graphs and networks. And I would like to give an example of social networks like Facebook or Twitter, where basically we have a huge graph. At Twitter, it's hundreds of millions of users and multiple billions of edges that connect these users. Next, please. And again, here we can apply deep learning models that take into account the structure of the graph. So basically, we can do deep learning on graph structured data. And one application that was mentioned, and that was a company that I was involved in, was looking at how fake information spreads on the web, or in particular on social media. So there are many empirical results that show that fake news, however you define it, that's a little bit controversial topic, how exactly you define what is fake and what is not. But they spread differently on social media for a variety of reasons. I think it's not even clearly understood. But what we asked is, if we have examples of what could be, by some definition, considered fake and not fake, can we actually learn from the spreading patterns only whether the story is fake or not? So this is potentially, this is a very powerful idea, because you don't need the content itself. It doesn't actually need to be the content, let's say, of Twitter. It can be a YouTube video. If you look at the way that it spreads, it can provide some extra information that might help in identifying the type of content. And here I have an example of inflammatory tweet from a prominent politician in France, and how it is retweeted and picked up by different people. Next, please. So basically, you see a kind of, well, talking about infectious diseases now with the new coronavirus, right? So it's a kind of infection that spreads on the social network. Basically, you have a cascade of, it starts from one or multiple users, and it is retweeted and spread over the social network. And by looking at this cascade and associating some ground truth label, we used sources such as PolitiFact, which are professionally verified stories, basically by journalist fact-checkers. We could create a training set on which we could train these geometric deep neural network models and decide whether, basically train a classifier that would predict whether a story is true or fake. And we achieved actually a highly accurate performance. That was a company that I was involved in with my students, called Fabula AI, that was acquired by Twitter last year. And you can see here my collaborators, my former students, who are now part of machine learning team at Twitter. Next, please. So let me mention one thing that that we are working on, and it actually relates very much to the previous talk. And these are recommender systems. So if you think of recommender system, basically it's some algorithm that tries to show you content that you are likely to engage with or spend more time. Next, please. So Netflix is a good example, where there are probably tens of millions of users and multiple hundreds of thousands of movie titles, and you try to predict whether a user will like a movie or not. Next. So you can think of it as a kind of huge matrix with numbers. So the numbers tell, let's say, a score, whether the user likes a movie or not. And you try to fill in this matrix with missing numbers, right? Basically, try to interpolate. So what we see that if you incorporate some graph structure, some social relations between users, or some similarity between users, this becomes a much more accurate recommender system. So you can predict much better what the users might like or dislike. Next. And next again. We can skip this. Yes. And this as well. Yeah. So basically what you end up is constructing with geometric deep learning algorithms is a kind of low-dimensional representation of the users that can be then matched to representation of the movies or any other items. And one of the challenges, for example, how to make it scale, how to make it work with huge graphs of web scale. Next, please. And next again. And also how to account for the dynamic structure of the network, how to account for the dynamic structure of the human tastes, right? We evolve, the social network evolves, everything evolves. So it's not just a single point in time, it's a representation that is dynamic. So we need to account for different behavior in time. Another class of applications come from biomedicine. So this is something that I'm working on in my academic work. Next, please. And this is just very recent. 2 days ago, our paper appeared on the cover of Nature Methods. So we use geometric deep learning technology for protein design. So I don't know how much you know about proteins, but basically these are the most essential molecules in our body. Basically, all life we know on Earth and elsewhere, because we don't know any other forms of life, is based on proteins. So proteins responsible for structure, for messaging, hormones. Hemoglobin is also a protein molecule that carries oxygen to our tissues. Also, many diseases happen because something a pathogen binds to a protein or disrupts the way that proteins interact together. And many drugs work by the fact that we develop a molecule that attaches or binds to a protein and does something in the body, whether it disrupts or activates some chemical reaction. So predicting how proteins interact with each other is absolutely crucial for development of drugs. In this case, what we are trying to do is to develop binders for oncological immunotherapy. So I don't have time to go into it, but I will be glad to talk about during the break. And this is the cover of Nature Methods with a beautiful design. So talking again about drug design in general, if you think of the space of potential candidate drugs that will cure you from cancer or any other disease, estimates vary, but the number of synthesizable molecules in the lab is more than the number of atoms in the universe. It's 10 to the 60 at least. It's absolutely unimaginably large number. So obviously you cannot test each such candidate in the lab, right, experimentally. So in order to deal with this problem, people resort to experiments. So you can do quantum mechanical simulations to see how, for example, a molecule will bind to a protein. You can do some simplified version of these experiments. So this is still computationally intensive. You can probably virtually screen maybe millions or billions of candidates this way. So with graph neural networks, with geometric deep learning, it can be done about 4 to 5 magnitudes faster. And these are results from DeepMind from 2 years ago, so it's probably even better nowadays. And this opens potential revolutionary capabilities in drug development and drug design. You can predict properties of molecules, of candidate molecules. You can also, in principle, use generative geometric deep learning models to generate new drugs. So you can say that I want a drug with this set of properties. Please generate for me a molecule that does it. Right? And there are some initial results. It's a much more difficult problem, but there are some initial promising results. And actually, I'm aware of at least one case. It's not a drug design, it's a material design. It was a collaboration of my colleagues at Harvard at that time. Now they're in Toronto with Samsung, and they developed a new light-emitting diode using these methods. Next, please. So talking about drugs, still, if we just look at the number of FDA-approved available drugs on the market in the US, we're talking about roughly 5,000 different drugs. Now, it happens that not all drugs work perfectly, right? So if you take a drug, especially against some serious diseases, it will usually come with some side effects. So you will take another drug to counter the side effects of that drug, and maybe yet another drug to counter the side effects of the second one. Bottom line, we take multiple pills at the same time. And also in many complex diseases, it's not just one thing that you're trying to cure. It's a combination of many different symptoms. Now, if we look at just pairwise combinations of these 5,000 drugs, we are talking about more than 100 billion pairs. And the side effects of this combined therapy, what is called polypharmacy, is not fully researched. It's impossible to research all the 100 billion possible combinations clinically. And some side effects are known. So if you take a drug, if you look at the leaflet that comes with it, you will see that it has maybe some innocuous side effects, and some of them can be life-threatening. So if you want to faster deliver the drug to a market, you want to at least try to predict some of these side effects. And you can do this with geometric deep learning. So that was a very interesting work from collaborators at Stanford. And they basically looked at multiple graphs or multiple networks. So the protein-to-protein interaction network roughly describes the way our body works. Basically, that's how proteins bind together. The drug-to-protein interaction, can you go back, please? The drug-to-protein interaction network describes how drugs work. Basically, they bind to different proteins in our body. And they try to predict edges, basically, that represent drug-to-drug interaction, essentially the side effects, and the probability of them happening, and also the kind of side effect and the seriousness of this side effect. So we try to take this idea to apply it not to drugs, but to foods. And basically, we can model the effect of a drug on our body as basically a signal on this protein-to-protein interaction network, protein-to-protein interaction graph. And basically, by using this information, employing graph neural networks, geometric deep learning algorithms, we are able to tell whether a molecule is drug-like from this binding signal. Next, please. And basically, this allows us to train a classifier that depending on what kind of data set we train it, we can predict, for example, oncological drug likeness for a molecule. And if we apply it now to a different set of molecules, for example, molecules contained in food, we can predict which kinds of foods will have drug-like effects, and in particular can be potentially helpful in dealing with cancer. Next. So we know that many foods, especially coming from the plant kingdom, contain molecules from chemical classes that are similar to drugs that we find, for example, in cancer therapies. Obviously, in much smaller doses, but we can actually map these foods. Next, please. And we found, so we call this the food map. We found that there are some prominent champions, what we call hyperfoods, in this map. And for example, very boring foods like green tea or maybe celery or cabbage contain many molecules from classes that have high drug likeness to oncological drugs. And I hope that I convince you that this is just a tiny bit of what can be done with geometric deep learning, with these network-based artificial intelligence algorithms, applications ranging from social networks to computer graphics, computer vision, biology, high-energy physics. We have collaborations with high-energy physicists. If you think of Large Hadron Collider, basically it bangs particles at near the speed of light, and it creates jet of different new particles that are born as a result of this collision. So you can describe these jets of particles as graphs, and you can classify interesting events. So we used it for neutrino detection. So that's another experiment in high-energy particle physics, where it significantly improved the detection accuracy of astrophysical neutrinos. So that's completely kind of science that is probably hard to commercialize, right? So that's more for the understanding of how the world around us works. So in the last few minutes remaining, let me talk briefly about a couple of challenges that we are currently facing with this technology. Next, please. So one thing is the question of hardware. One of the driving forces of the deep learning revolution was the computational power of graphics hardware that happened to work well for these kind of neural network architectures. We don't have something similar for graph structure data. And there are multiple companies now actually working on developing specialized processors that will be able to organically deal with graph structure data. Dealing with large-scale graphs, like those at Twitter or at Facebook, is a big challenge. Some of the algorithms that are developed in the research community would not easily scale up to these settings. Dealing with graphs that change in time, like a social network that is dynamic. Protecting against adversarial attacks. So this is an interesting topic. I didn't have time to talk about it, but same way as you can disturb some and fool some system, obviously you can fool machine learning systems. And actually there is an entire field of research that tries to understand how to attack a machine learning system in a special way. So you want the machine learning system to produce some desired output, so you can feed it with specially designed noisy information that will affect the way that it works. So it is especially interesting and especially challenging when dealing with graph-based machine learning systems. No, back please. Not yet, almost. Challenges in privacy. So I will mention just one example. I think in the previous talk, we all heard about the potential pitfalls in metaphorical and even literal sense. So dealing with privacy, the graph structure contains a lot of information about the users. So even if you think that you anonymize the data, you remove all the user-specific information, you publish the relations between users, the relations allow to reveal a lot of user-specific data, even though the data is not contained there. So the one example that we've been working on is de-anonymizing phone call networks. So if I have records of calls between different users, even if I completely remove all the user information, it's just a graph of phone calls, I can re-identify the users, for example, in different periods of time. So basically, I can tell you that it was you with high probability that called these people, even though I have nothing about you at all. I just know these transactions. And this is very important because some social networks, such as Twitter, for example, by its nature, it's an open social network. So you can download Twitter data, Twitter graph, through their web interface, and potentially have access to or you can recover private user information. There are many interesting topics about theoretical guarantees. So this is more academic, basically how powerful graph neural networks are, what kind of problems they can solve, what kind of problems they cannot solve. But I think what is probably the most important message is that with these algorithms, we're trying not to develop a black box that will serve everything. It's impossible. You want to incorporate domain-specific knowledge, your understanding of the problem, in order to to achieve the best result in the field of application. So I think I will stop here. We'll be glad to answer any questions. Thank you.
And we will have time for 2 questions. So let's take the one that has the most upvotes, which is, after deepfake technology, can we ever believe our eyes again?
Well, a very good question. So I think it's an adversarial game in the sense that basically the technology that counters the deepfakes. So deepfakes, for those, I believe everyone knows, but basically this is computer vision or computer graphics technology that produces lifelike images or videos. So you can take a video, for example, of Barack Obama and engineer it in a way that Barack Obama speaks about something that he has never spoken. So basically it's completely synthesized and completely fake. So there are methods that try to detect these doctored or engineered videos, but it is becoming harder and harder. Basically, these methods are already completely realistic. They are actually used in the movie industry. I think there was a recent movie called The Irishman, where this kind of technology was used, and it is completely photorealistic. So I think the short answer, no. I think we cannot believe our eyes. I think we should rely on, rely on our critical thinking, maybe compare information. And social networks are also trying to do it. So Twitter just yesterday announced a new policy about deepfakes, not only making it illegal, but also in cases where this kind of content can be detected, it will be marked as potentially harmful or as potentially manipulated.
Fantastic. So let's take one last question, and I'll let you actually choose the question you would rather answer. So do it the other way around.
I will take the second one. So about deep learning. So I don't know, first of all, the answer to is. So deep learning now has expanded to encompass a lot of different things. I think what will change is definitely, what will remain and what has changed forever is data-driven approaches. So basically methods that rely on massive amounts of data. Now deep learning, it's already not about neural networks in the narrow sense, but it's about what people call differentiable programming. So basically, if you can describe your algorithm as a computational graph, you can make it learnable. You can do what is called in this field backpropagation. So you can backpropagate through things that do not look at all as neural networks. It can be computational algorithms. It can be practically anything. So I think the short answer, I have no idea. The long answer, probably it will be somewhere, maybe in different flavors or in combination with other methods.
Thank you so much.